Hey guys, welcome to the first video of 2020, and today we're going to have a look at how we can do intent recognition using BERT. And more specifically, we are going to fine-tune the BERT model using a custom dataset that contains 7 different intents, and those intents have around 2k or 3k, I'm not so sure about that, examples, short texts that should be classified into one of those 7 intents. The data comes from GitHub actually, and it's based on one paper which is called, let me show you, SNP's Voice Platform, an Embedded Spoken Language Understanding System, yabba dabba dabba. So the dataset is actually around a year and some months old. So this dataset is actually contained on GitHub. So what I did was to clone this repo and get the examples. As you can see, they're in JSON files. I did some pre-processing offline, and those examples are actually now in nice little CSV files. So we are going to have a look at the data, but please keep in mind that the data that I'm going to show you and that you can also download as well is a bit pre-processed, and I'm not going to show you the pre-processing steps because they're simply boring. So now that is pretty much done, let me just skip to the notebook in here and show you what I've already did. So the first thing I'm going to do is to actually check what is the GPU that we will get for this tutorial. And while this is connecting, I'm going to queue in the installation of TensorFlow GPU. This will install the latest version of TensorFlow GPU. And that's, I believe, let me check. Yeah, 2.1, I believe it's the latest version. So yeah, we will install this, and I'm going to install the grco or whatever, grpco, which is required for our dependencies today. I'm going to install tqdm for the progress bars, another library which is called BERT for tf2, and this is required because unfortunately the original implementation of BERT that is provided by the Google Brain or Google research team, I'm not so sure about that, is actually not compatible currently with TensorFlow 2. So there is this package BERT for TF2 that allows us to use the pre-trained BERT models with TensorFlow 2, and I'm going to show you that right now. This is the package. It's done by somebody at GitHub with the username of KPE. So thank you, man, or girl, whatever. So yeah, you can have a look at this package. It's really well developed, and I think it's really good that it and it's a really good thing that it supports TensorFlow 2. There are actually examples in here which is based on sentiment analysis for movie reviews, and you can have a look at those too if you want to have a look at that. Okay, so now that pretty much everything is installed in here, let me just did this as well. Okay, so after that I have a bit of imports, and those imports are actually based on pretty much pandas, numpy, tqdm, the standard stuff. We are importing Seaborn, Matplotlib, and configuring the plotting stuff in here, and also we are setting the random number generators. But the new thing in here is that we are importing BERT. We are importing a BERT model layer, which we are going to use in a bit. We are going to import the way that we are going to actually load the pre-trained BERT models, and BERT also comes with its own tokenizer, which is really great, so you don't have to actually do much of a pre-processing of the text yourself, and you'll see in a bit how we can do that. Okay, I'm going to execute this cell, and this should work out very good. So the next thing that I'm going to do is to download the CSV files that I've already discussed. And again, those CSV files contain the intents and the short text that are required for the intent recognition task. And if you are not familiar with the intent recognition task, it's simply given a text, and usually that's some user query. So let's say that a user is coming to, let's say, Facebook or a Google form, and he's typing in like, I can't log into my account, let's say. And the job of the intent recognition model or the intent prediction or the intent recognizer is to assign some one or maybe multiple categories to this intent. So for example, in this case, the intent might be something like user or forgotten password or something like that intent, let's say. So okay, let me just download these files, and this should be pretty quick. Okay, so we are done with this. And the next thing that I'm going to do, of course, is to use pandas to load the CSV files. And I'm going to load those in here. And let me show you that these files are actually in the main folder, downloaded in here. Here they are. And I'm going to load all of them. Okay, so the next thing that I'm going to do is actually to merge the training and the validation data, because we are going to use Keras for training, and we're going to use the validation split or whatever to say that to Keras that we want some percentage of the training data to be used for the validation. So we're going to actually extend the training data that we have in here, and I'm going to just append the validation data to the training data, and I'm going to reset the index so that the index is actually quite nice. It starts from 0 and goes all the way to the number of the rows in the data frame. Okay, so I'm going to have a look at how many actually training examples do we have, and I'm going to use the shape thingy, and we have right around 14k examples, which is great. But remember that we have 7 different intents. So the first question that you might ask or you should ask the first question in this situation is, well, okay, I have 7 intents. How representative is the distribution of each different intent? So do we have class imbalance in here? But let me show you, before answering that, let me show you the contents of a sample data frame in here. Okay, so as I've already discussed, we have the text, which seems like a relatively short thingy text. Yep, and we have the intent. And again, you can think, basically you can think about intent recognition as text classification, or maybe text tagging, because in some cases some intent might be insufficient and you have to assign multiple intents to a query. So as I've already said, we are going to have a look at how representative of a sample we have from each different intent. So for that, I'm going to use the Seaborn's count plot method or a function, and I'm going to create a chart using that. I'm going to pass in just the intent, and I'm going to use the color palette that we have in, actually I've defined this like right over here, and those colors we're going to have a look at them in a minute. So the next thing is that I'm going to say the title of this chart, number of texts per intent, or examples per intent might be a better one. And the next thing that I'm going to do is to rotate the labels, because if I execute this right now, as you can see, the labels are not quite readable. So I'm going to show you a way to rotate the ticks or the x-axis labels, and this is taken from I don't know, somewhere from Stack Overflow. I'm not sure about the source of that one, but it should work like this. So you basically have to just take the x-ticks labels that we already have, or it won't work, I've tried, and specify the rotation of the labels. Rotation, and we want a 30-degree rotation in here, and we are going to do the horizontal alignment. I can't write right now, so we want to be right aligned, and you'll see the result of that hopefully. And I'm going to put semicolon at the end, so the output is just the chart. And voila, as you can see, we have each label slightly tilted based on the degrees that we've specified in here. And most importantly, you can see that pretty much every intent has roughly the same number of examples in it, which is great because we don't have to do anything like doing some sort of imbalance method stuff in here. Okay, so this is great, and this is pretty much all of the, let's say, exploratory data analysis that we're going to do so far. And the next thing is actually we are going to download the pre-trained BERT model. Actually, I guess every BERT model is pre-trained, but you might ask yourself, what is BERT? So in the tutorial that I will link down in the description, I'm going to link this couple of paragraphs explaining what BERT is from a really bird's eye view. And this is just an overview, but one of the best sources of understanding what BERT is actually the BERT paper, which is BERT pre-training of deep bidirectional transformers for language understanding. And this paper is actually very well written, and it's freely available on the archive, of course. And it's worth checking it out. But another very good resource that I found, and it's probably recommended by a lot of people, is the article The Illustrated BERT, and this one is called this one is written by Jay Alamar. Thank you, man. This really gave me a very good intuitive understanding about what BERT is and the process, the history behind how this model actually came up to be. So please, if you wanna get a understanding of what BERT is, go and check those resources. Of course, there are many great tutorials out there, and I'm by no means expert in BERT or NLP or whatever, but I think that it's very important to understand the way or the path that led to developing the BERT model, and some of the really important milestones in the NLP or the NLP community as a whole are the ELMO word embeddings and the transformer model itself, and I'm going to talk about those in a little bit. But the Illustrated BERT, ELMO and Co. Article or tutorial is like really good if you want to understand, and they have these and this guy made those visual diagrams on which you can have a very good understanding of what those stuff is really. So what is BERT? BERT is actually a pre-trained model which is based on the transformer encoder, and there are actually two pre-trained versions. that are trained on the Wikipedia dataset. So you can think of this as like the whole Wikipedia text, which is something huge, I guess, and the book corpus dataset, which is you can find in this paper. And this again is really large dataset. And the model actually comes into two flavors or two versions. The base BERT model is composed of 12 encoders, and the large one, which broke, I guess, every NLP task out there, has a large. The large model has 2 times the encoders, 24. So today we're going to have a look at the small one, because it fine-tunes faster. But in the real world, you might want to have a look or fine-tune the larger one. And again, the base or the small one is not small at all. It has it has around 110 million trainable parameters. And this is just huge, like really huge, at least for today's computing capabilities. And the next most important thing that you need to know about BERT is that it's based on 2 very, very good ideas in the NLP from the NLP community. One is the ELMO contextual and word embeddings, and the other one is the transformer model. So again, if I go to the illustrated BERT article, this guy did a great job of showing just a picture and letting you know what actually ELMO is. So in the past, actually, when you got some word embeddings, you got a vector, and this vector was like some static representation of this word. What ELMO did is like, well, of course, the meaning of a word depends on the words surrounding it. So you have to give me the context to understand what this word is used and where it is used. And then I'm going to show you the embeddings for this word. So you can read this one. Hey, ELMO, what's the embedding of the word stick? There are multiple possible embeddings. So there are multiple meanings of the word stick in here, and you have to basically use it in a sentence. So what this means is that you have to use it and check the words surrounding it to understand the meaning of that. So this guy is giving example, and when the example is given to the word surrounding this word of your interest, so then you can get an embedding that is specifically done for the words surrounding it. So basically the embeddings are no longer just single vectors, they're more like matrices, so they're 2D, I guess. Okay, so this was the ELMO, and the next big thing, I guess, was the using attention mechanisms. And actually the attention mechanisms is used in the transformer model. So there is a paper in here for that one as well. Attention is all you need. It's from the Google Brain team as well. So they represent the first transformer model that uses attention in NLP. I'm not sure if that's the first model, but it's really the model that was presented and gave the NLP community the idea that, well, attention is all you need, and you don't need LSTMs, and actually attention is much better at remembering long-term dependencies between words. So the problem before that, I guess, was that when a model was like reading a text, the model kept forgetting what the text was about, like, let's say, a few paragraphs before. So what the transformer did was to actually kind of eliminate this problem, and now you can use just a transformer instead of LSTMs to keep those long-term dependencies. So the most important thing that the BERT model actually did was to do bidirectional. The BERT is a bidirectional model, so it most of the previous transformer models did like only backward understanding of the text. So the BERT model is basing his attention on both what has come in the text before and what is coming in the text next. So it looks forward and it looks backward to understand the context or the meaning of the words that he is currently looking at or he's posing his attention on. And to be quite frank, I don't think that anyone thought that the BERT model will do this amazing, be so successful in the NLP community. And I don't think that anybody understands exactly how BERT is so good. And I'm going to show you that BERT is really good. The next most important thing about this BERT model is that it's really easy to fine-tune based on the task that you have. So basically, you just take the pre-trained model and you can swap on some layers on the bottom of it. And basically, you have pretty much state-of-the-art NLP model that most likely will blow up everything that you had like 6 or 10 months ago. Like, I'm going to show you how we can do that. And yeah, let me just begin with downloading the BERT model. The BERT model will be downloaded from here. This is the original Google Research repo, and it contains, as you can see, multiple models in here. And of course, those models are provided by the Google research team themselves. And keep in mind that this is only TensorFlow 1. So we are going to use the BERT for TF2 package, but we are going to download the model itself from the original download links provided in here. Okay, so let me start by doing a new paragraph in here, and I'm going to say intent recognition with BERT. Okay, so I'm going to download the model and I'm going to copy the link. Okay, we're downloading this, and you will see that this small model is around 400 megabytes, which is insane in my opinion. But yeah, this is the small one. And I'm going to unzip the file. And again, the file is locally stored in here. This is the uncased, so no, this is just lowercase, I believe. When you unzip this, you see you will get a checkpoint, a vocabulary, which is going to be used for the tokenizer that comes with BERT, and a BERT config JSON, which contains basically the configuration for importing the model. And if we open this, you will see that we have exactly some sort of configurations. This is the number of hidden units in the layer, and as you can see, we're using 12 heads, or the 12 decoders that we have already spoke about. This is the base model, and in here you can see that this model has around 30k in his vocabulary. So all of those are something that you might understand just from having a look at the config file. Okay, so now I'm going to make a folder called model, and I'm going to move this folder in there. So it's a bit easier for us to understand what is happening. And I'm going to use the make dirs. I'm going to move everything from the folder that we've downloaded to there. So it's a bit easier to understand. Yep, we have the model in here. And then I'm going to specify the model name, which is basically this. Okay. Then I'm going to specify where is the checkpoint directory in here. Model and the BERT model name. Then I'm going to specify the checkpoint file itself. And this will be BERT model dot checkpoint or CKPAT. And the last thing that I'm going to do is to specify the configuration file, which is the JSON that we had a look at. Okay, so now we have all of this. Let me check if those are looking all right. Yep, that looks fine. BERT checkpoint file. Okay, this looks quite all right. So the next thing that I'm going to do is do some pre-processing, and in here we're going to use the Tokenizer that is provided by the BERT package. And I'm going to create a class that basically does the pre-processing for us. So this will be a little bit more generic and a little bit more reusable, but I'm going to explain why we did and how we did stuff in it, but it will be just a big blob of code with just two private or protected, whatever you want, methods. So let me have a look at, let me show you how we're going to begin creating this class. And after we create this class, the next couple of things are going to be really easy to do. So let me start by creating the class, and I'm going to specify this as intent detection. Maybe a recognition is a better name in here, data, but whatever. And I'm going to specify the data column, and this data column actually is coming from here. The data column is actually the text column, and the label column is the intent column. I'm going to specify a constructor, and in this constructor I'm going to do most of the work by using two helper methods, which we will build in a second. So this thing is going to get a wide variety, a large amount actually of parameters. We're going to take the training set, the test set, the tokenizer, the class names that we have, and the max sequence length. So why do we need this max sequence length? Well, basically most of the NLP models can work with a fixed number of tokens, or each sequence should be a fixed number of, each sequence should have a fixed number of elements. So as you can see, those texts are from a wide variety of lengths, and of course we need to do some pre-processing and make sure that each text or each pre-processed example or sequence is a fixed set or a fixed number of has a fixed number of elements. So to do that, we are going to basically specify a parameter which basically cuts sequences that contain more elements that we specify, and for those sequences that are less than this number, we can just pad those with, for example, zeros. So the padding actually increases the number of elements in the sequence, but it increases it using a dummy element, which our example will be 0. So after that, you can take a batch of this data, and the batch is going to be to contain the same number of elements and you can use that to train with your already recognized optimizers. So basically we need to do the padding because otherwise the optimizers won't work, and I'm not quite sure if actually the BERT model can work with non-fixed or flexible number of elements in the sequences. I know that you can use, for example, LSTMs, and those can work with flexible number of parameters, at least in PyTorch. But maybe not in Keras, I'm not sure about that. Anyway, we're going to do the padding, and we're going to cut the longer ones if that's necessary. So the next thing I'm going to take in here is the tokenizer, and I'm going to specify the type. As you might already know, in Python you can specify the type if you're using a high or a recent version of Python. I'm going to take the classes. Those will be just the name of the intents, and max sequence len, which is going to be 192. Okay, so now that we have this, I'm going to assign those to some fields. I'm going to assign the max sequence length field to 0 at first, and you'll see why in a second. And I'm going to take the classes. Okay, so the next thing that I'm going to do is create the training X and Y frames. So those will be actually NumPy arrays, and in our case we are going to do this for the training X and Y's. So the X will contain some vectors or some sequences, and the train Y's are going to be the labels, which are something from 0 to 6, including 6, because we have 7 different intents, and those will be the target or the classification, the target labels for our model. So how we are going to do that? I'm going to take this, and I'm going to create the field train X, train Y, and I'm going to take the test X, test Y, and I'm going to map this using a method that we haven't already created, prepare, and I'm going to map this over the training and the test data. Okay, so we already have something that we haven't defined, but that's all right. After we do the preparation step, I'm going to calculate the real max sequence length, because you are specifying the maximum sequence length in here, but it might be the case that none of those are actually that or longer. So in that case, you wouldn't really want to create such a huge sequences, because those will be just using memory it will be inefficient, and your training will be slower than it should be. So for that reason, I'm going to take the maximum sequence length that will be calculated in the prepare method, and note that this sequence length is calculated from both the training and the test data. Okay, so we now have the real sequence length, and after this is complete, I'm going to do the padding. And the padding, of course, is going to be done only on the sequences which are already transformed into something else, and we're going to see how is that done. I'm going to call the padding method, and again I'm going to call this on self-train. I'm going to call this on those arrays. Okay, let me save that. Okay, so once again, taking the tokenizer, initializing the max sequence length to 0, not taking this from here, then setting the classes, calling a method prepare that we haven't defined yet, calculating the real max sequence length, and then we are doing the padding in here. So the next two things, of course, are going to be defining those methods, and let me start by defining the prepare. And it takes a data frame as a parameter. We are going to initialize two arrays, which are the x's and y's, and in here I'm going to iterate over each row in the data frame, and I'm going to use TQDM to follow the progress of that. Okay, so the first thing that I'm going to do is to extract the text and the label from here, and I'm going to do that using intent detection data column, which again is just the text. And for the label, I'm going to do the same thing, but I'm going to take the label column. All right, so next I'm going to use the tokenizer to tokenize the text, of course. And I'm going just to call the method tokenize on the text. So now that we have the tokens, we have to actually apply or add two special tokens. The first one is going to be CLS, and this says that a sequence is starting, and then we're going to add a separator, which is a special token. So we will basically surround each sequence or each text with those special tokens. And you have to use those brackets to specify them and add the separation token. And then the next thing that we're going to do is to convert the tokens, and you will see what tokens are, into integers or numbers, because of course computers don't understand real text, they understand only numbers. So the tokenizer actually has a helper method to do that for us, which is really great. And those will be called token IDs. And the method is convert tokens to IDs. So based on the token IDs, we can try to calculate exactly the max sequence length, and this is going to be the maximum between the current maximum sequence length and at the start this is 0, and the number of token IDs that we have in here. We can get the length or the number using the length method. Okay, so now we have a new maximum sequence length, or possibly the same number. And after that, I'm going to append to the axis the token IDs. And I'm going to append the index of the label to the y's. Of course, we're going to use parse categorical cross entropy, so we don't have to one-hot encode the labels, which is great. Thanks, Keras, for that, providing that. And yep, after all of this is complete, I'm going to return two numpy arrays for the x's and the y's. Save this. And yeah, we have the prepare method already done. And one side effect, which is something that I'm not really happy about, is from a software design practices standpoint, that this method has a side effect of calculating the maximum sequence length. But yeah, this is just taken from the example of the BERT for TF2. I've just modified it slightly so that you can basically use this on our dataset. And I think the implementation is a bit cleaner than provided in the example over there, but still this side effect is really something that is bothering me, and you might want to basically do something about it. The next thing that we're going to do is to define the path protected or private method, and this one is going to, remember, take just the IDs, because as you might have already guessed, in here the train thingy which already contains the token IDs, but not the tokens themselves or the text or whatever. So this will actually work with the IDs. And again, I'm going to initialize a vector called x, and after that I'm going to convert this to a numpy array, and I'm going to iterate over the IDs. I'm not going to use TKGM in here. I'm not sure why, but yeah, hopefully this is much faster operation. And yeah, after I'm iterating on this, on each ID, I'm going to do something that might look a bit strange, but this will basically cut the number of IDs that we have based on the max sequence length minus 2, because remember, each sequence has those two different tokens that are required by BERT. So we will basically ignore those, and I'm going to cut the sequence based on the max sequence length, or the minimum of the max sequence length, or the length of the input IDs, or the number of tokens or IDs in this sequence. So in this way you basically might not cut the sequence at all. And yeah, let me show you how this is done. I'm going to take the first elements, all of the elements until the minimum of this. Let me just extract this. It will be a bit cleaner, I guess. Until cut point. And this will be the length of the input IDs and the self max seq length. Okay, the autocomplete is good in here. So yep. So we are cutting until this point, which again is the max sequence length minus 2, the minimum of max sequence length minus 2, or the number of input IDs that we have in here. So the next thing that I'm going to do is to actually path the sequence until the max sequence length, so that it fills the max sequence length. So for example, if the max sequence length that we have is 30 and our sequence contains only 25 IDs or elements in the vector, we're going to add 5 more zeros so that the number of elements are 30. So I'll show you how this can be done. We're taking the input IDs so far and adding zeros at the back, and the number of zeros is going to be the self max sequence len minus the elements already present in the input IDs. So this will do the padding for us, and I'm going to append this to the arrays that we have, and this should pretty much do all of the data pre-processing for us. So let me execute this cell. It should work quite all right. Okay, so now that we have, this was basically the hard part, I guess, because yeah, the pre-processing is almost always the hardest part when doing machine learning or data science or artificial intelligence, whatever, deep learning, however you want to call it. But yeah, let me now start with creating this tokenizer. And again, this tokenizer is from the BERT package, and it's called full tokenizer, and it expects a vocabulary file and do lowercase. The default parameter is called is true. So remember that we are using the uncased version of BERT, and this version does not have casing, of course. So the vocab file is going to be the concatenation of the BERT checkpoint file, dir, sorry, and the vocab.txt. So this will be basically this file, model uncased vocab.txt. All right, let me execute this. And the tokenizer we can call the tokenize, which we are calling in here, but I'm going to show you how this is used. I can't wait to visit Bulgaria, of course, again. And as you can see, this thing lowercases everything and basically splits the tokens. It even split this one, and the punctuation is preserved. So this is a really good tokenizer that probably aims to preserve the punctuations and the let's say emotions when writing text. So the next thing that I'm going to do is get the tokens from here, and recall that the next method that we're calling is the tokenizer convert tokens to IDs. And I'm just gonna copy this, paste it in here, and I'm going to show you that what those tokens look like. And unsurprisingly enough, those tokens are basically numbers. So these are the IDs for each of the tokens that we have in here. And as you can see, even Bulgaria has a specific ID in here, which is great, I guess, if you're from Bulgaria, which, yeah, I am. So now that you know what the tokenizer does, let me just define a function called CreateModel, which will basically use the BERT, the pre-trained BERT model, and apply a couple of Keras layers to convert the BERT model into intent recognizer, basically. So let's begin by creating the function. And this function accepts the max sequence length in here and the BERT checkpoint file. And I'm going to open the BERT checkpoint file using TensorFlow. I'm going to open that for reading, and I'm going to use the config sorry, I also need the BERT config file in here. Yep, which I'm not passing as a parameter, which is really sad. Let me pass this as a parameter as well. So I'm deviating a bit from the code that I have, but yeah, this should be cleaner. And I'm going to read the config, stock BERT config, from JSON string. They have the from JSON file, but yeah, I'm not using that in here, which is sad. I'm going to read the config in here, and I'm going to take the parameters, map stock config to params. All of those functions and classes are from the BERT for TF2 package. And I'm going to specify an adapter size of none. And that adapter size is something that helps you actually fine-tune the BERT model faster. And there's a paper on that, but we're not going to use that in here because we don't have so much data, and we have the P stuff from the P100, yeah, P100 from the Google Co-op. So we're really lucky today. And finally, the BERT model is going to be BERT model layer from params, BERT params, and we're going to name this as simply BERT. Okay, so now that we have the BERT model loaded, which is basically one huge Keras layer, I'm going to specify the input layer from Keras layers input, and the shape of that is going to be the number of the maximum sequence length, or the sequence length, because yeah, every sequence that we pass in is going to be padded to this number. We've already did that. We're going to specify the type, which is going to be int32, and the name is going to be input IDs. The BERT output is going to be the result from calling the BERT layer on the inputs. And I'm going to print out basically the shape of the BERT, and you're going to see why in a second. BERT shape, BERT output dot shape. And just for the fun of it, I'm going to create this function, and this function implementation is not complete. But let me handle the sun in here. Yeah, let me just do this. Okay. Hopefully this is better for my eyes. I'm not sure. Okay, you're seeing my messy kitchen over there, but that's all right. So, if I call basically this thing over here, okay, this is not already done, but yeah, let me go through the trouble of continuing, and I'm going to show you a bit why I'm going to continue and why I'm showing you all of this. So we're going to take the classes, and those are just the unique intents, and I'm going to convert those to list, and I'm going to create the data preprocessor class, intent, detection, data that we've already defined. I'm going to pass in the training and test data, the tokenizer that we've already initialized, and a max sequence length of 128. And you should see some pre-processing happening in here, and for right about 3 or 4 or 5 seconds you have the training and the test data in here. So this is great. And if I call the CreateModel, which is again not complete, I'm going to pass in the max sequence length from the preprocessor, the data preprocessor, and I'm going to pass in the BERT config file and the BERT checkpoint file in here, and the loading is a bit slow, but that's all right. And as you can see, I'm showing you this because I wanted you to see that this actually has 768 hidden inputs or hidden nodes in the network. And from the config file in here, you can see this is the same number, the number of hidden units. So, but you're also witnessing that this thing in here has 38, a dimension of 38, which we are not very happy about. And the next thing that we are going to do is to actually take this and just take the zeroth or the first layer from here. So how we're going to flatten this? We are going to basically use the lambda layer from Keras. From this sequence, I'm going to preserve the first dimension, take only the zeroth element, and then I'm going to take all the elements 768 from the last dimension, and I'm going to pass in the BERT output to that. Then I'm going to attach a dropout. I'm using the Keras functional API in here. .5, and then I'm going to flatten this using the dense layer, and I'm going to take the widgets because this is the output from the BERT model, and I'm going to specify the number of units in here, which is going to be exactly this number over here. So this is why I've shown you this. And this number should be specified, yeah, in the name, yeah, in here. So the hidden units is also in here, but whatever, we've already seen that. And I'm going to specify the activation function TANH, and I'm going to pass in the widgets or the class outputs. I'm going to do another dropout layer with 50% probability for each unit, and finally we have the output layer, which is going to be again a dense output layer. The activation is going to be softmax function because we are doing a classification, and the number of units is actually going to be the number of classes that we have. So this pretty much should be the architecture of our model, and the model is going to be a Keras model, of course. The input is going to be the input IDs, and the output are going to be the widgets of the final layer, which is doing the text classification for us. I'm going to call the build method in here and specify the input shape of this whole model, which is going to be none for the first parameter because the batch size is going to be automatically inferred by Keras for us, and the max sequence length. The next thing that I'm going to do is to load the weights, which will be a bit slow and probably the hardest part on our CPU, and I'm going to pass in finally the BERT checkpoint file, and I'm going to return the model. So finally this whole thing is done for us. Let me call it. So now it should take a lot more time, and yeah, we have an error in here. So this thing called input, where did I say input? Let me check. BERT model inputs. Okay, so hopefully this was the mistake. let me rerun this. Keyword argument not understood. Inputs and outputs. Well, this should be right. Okay, so inputs and outputs, yeah. And as you can see, we have some unused weights, but yeah, this should be just fine, I guess. So let me just show you what we have in the training data. Data train X. So the shape of our sequences. And if you recall, we specified a maximum sequence length of 122. And as you can see, we have only 38 elements in each sequence, because yeah, the sequence, no sequence was greater than this number, had more elements. And let me show you the Y data. It's just 0 for the first element, so these are just the classes. 1, 2, okay. Yeah, you get the point. Okay, so let me show you what a sequence looks like. Just the IDs with the padded values. And train text 0. So this is the sequence. Listen to Westbam album Allergic on Google Music. And if you count the number of elements, but split those. We have 8 elements. 1, 2, 3, 4, 5, 6, 7. Yeah, but the tokenizer is not doing the same thing as splitting by space. Okay. Why this is the case? Let me see. Yeah, but we have the 2 other tokens. So 5, 6, 7, 8, 9, 10. Okay, let me go through the tokenization of this one, because this is interesting. Let me tokenize this. So yeah, this gave me more tokens for some reason. 3, 4, 5, 6, 7, 8. This is more, yeah. So basically the tokenizer is adding a bit more tokens, yeah, but as you can see, those numbers are in the sequence in here, and those are just the special tokens, I guess, that we've already defined. So yeah, the tokenizing stuff really works, I guess. And we have the data that is now ready for well, recognizing intents. Let me just show you, before starting the training process, a summary of the model. And as you can see, we have almost 110 million parameters. The BERT layer itself has roughly 109 million parameters, which are trainable. And recall that this is the small one. The big one should have at least twice as much parameters, or maybe even more. And the architecture from that point on, it's really simple. The R1 layer, which basically takes just the widgets or the first layer from the output, or flattening the output of the BERT layer, so this is basically the BERT model is again just a stack of, let me show, just a stack of decoders, and we are taking the element from the top of the stack, which is basically the result passed through all the encoders and probably the thing that we want. Okay, so we have the dropouts, the dense layer, first hidden layer, then again a dropout, and finally we have the output layer, which contains only the number of classes that we have, which is 7 in our case. Okay, so the next thing that I'm going to do is compile this model, and this model from this point on is really just an ordinary Keras model. So you can basically save it as an H5 file, or maybe wallet, deploy it to production, whatever you want to do with it. But let me start with compiling it, choosing an optimizer. I'm going to go with Adam, and I'm going to use this tricky little number as a number in Python. Let me see how I can we do this so I can show you the value of this. You should hopefully understand that this number is really small one. Okay, so this is basically the warning rate that we are specifying. It's really a small number, and this is one of the numbers that is recommended when fine-tuning the BERT model by the authors of the paper themselves. I'm going to specify the loss, and I'm going to use the sparse categorical cross entropy because again we don't want to do one-hot encoding in here, and we're just passing in the widgets. And for a metric, again I'm going to use the sparse categorical accuracy. And I'm going to say that this will be from accuracy abbreviation. So let's compile this, and now that the compilation is done, I'm going to use a TensorBoard callback so we can have a look at the training process during with TensorBoard after everything is complete. And I'm going to specify a walk dir, walk intent detection, and I'm going to pass in the datetime now, and format this with this formatting. I'm not gonna write this because I'll mess it up. I'm just gonna copy and paste it in here. So this is the walk directory, and I'm going to create a TensorBoard callback, which is implemented in Keras. Of course, walk dir is going to be the walk dir. I'm going to finally fit the model. I'm going to do a validation split, which is going to be the 10% of the data that we have. Batch size, which is again another recommendation from the BERT authors, is going to be 16. I'm going to shuffle the sequences. I'm going to train for 5 epochs, which is again something recommended by the BERT authors. And this suggests that you don't need to fine-tune the model for long to get good results, and you see in a minute that this might really be the case. And specify the callbacks themselves. And yeah, this should pretty much be all of that. And I'm going to start the training process. Okay, so let's just wait and see if this works out. Okay, the training has started, and I'm going to pause the video and resume after all of this is complete. And welcome back. And the training is complete. And as you can see, the numbers are actually pretty insane. I mean, like at the first epoch, at the end of the first epoch, we have a validation accuracy of more than 97%, which is absurd. That's crazy. And as you can see, the model is has started to do some overfitting at epoch 5, but recall that we have like really huge model and not so many examples. So again, we have a validation accuracy at 98.5% at the fifth epoch. And as you can see at the P100, the training time was not that long. So yeah, you can basically train with your own examples, and I think that BERT is a really amazing model. So let's evaluate the test accuracy on the test set that we have. We are going to use the model, call the evaluate method, provide the test data that recall that this model haven't seen, and I'm going to print it out. Alright, 97% accuracy on the test set, which is great once again. And I'm going to take the predictions from the model and argmax those. So basically I'm going to take the class that is most likely to be the correct one based on the model's opinion. And I'm going to print out a classification report of the predictions and the real values. And I'm going to specify the name of the classes in here as well. And as you can see, the precision and recalls divided by class and the F1 score are really high. So once again, this looks really good. And there is a sample confusion matrix that you can have a look at the blog post, and I'm not going to redo that in here because this video is already very long. And as you can see, the classification report in here at least is again extremely good, and this of course is based on the fact that the model is very accurate. And the next thing that I'm going to show you is basically do some sentences that the model hasn't seen, and basically how you can use the model once it is deployed, and maybe you can load the model and then provide some sentences that some user or queries from the user and obtain some predictions from the model. So I'm going to specify 2 sentences. And the first one is going to be play our song now, and then rate this book as awful. Let's say those are the examples. And first I'm going to get the tokens. I'm going to use the Tokenizer for that. Then I'm going to append the special tokens CLS and SEP. All right, and I'm going to do that over the tokens, and I'm going to get the token IDs using the map function again, and the tokenizer convert tokens to IDs. All right, now that we have the token IDs, I'm going to path the token IDs. Using the max sequence length that we have from the data preprocessor. And I'm going to convert that into a NumPy array. Get the predictions from the model. Let me just run this. So yeah, I have an error in here. Okay, so this should be all right. Let me print out the sentences and the predictions. So the text is going to be the text. I'm going to print out a new line. And print out the intent. Now let me do this actually. The intent is going to be the classes label, because these are just the integers. So for the play our song, now we have the play music, which is great, and rate this book as awful, which is rate book. Okay, so let's have a look at the intents once again, and maybe try a bit harder example. Reserve a table for two, maybe should be book restaurant. Reserve a table for 2. Let's try this one. And again, book restaurant, which is great. Okay, so this is how you can use your already trained model on your own dataset and use this basically those couple of lines to get predictions in production. And let me just mention that actually Hugging Face Transformers package is probably the best package out there that is composed of state-of-the-art natural language models, and this one is compatible with PyTorch and TensorFlow. It has pre-trained BERTs, GPTs, Roberta, DistillBERT, and many more transformer models. And speaking of PyTorch, well, this will probably be the last video that I'm doing, at least for now, on TensorFlow and Keras. And starting from the next video, we're going to have a look at getting started with PyTorch, doing some object detection with Detectron 2, building neural nets using pre-trained models. Hopefully, I'm going to use some of those packages like the transformers from Hugging Face using PyTorch, and all of those are coming in the next couple of months. I guess that I'll try to at least post a video or two every week so that you guys are keeping with your warnings and deep warnings. So thanks for watching. I know this video is really long, but yeah, actually playing with BERT is really rewarding, because yeah, probably your final results will be amazing. And let me know in the comments down below. Please subscribe, share, like this video, and hopefully I'll see you in the next one. Bye bye.